everyone, welcome back. In this video, we'll introduce joint distributions, or models for two random variables. We'll begin by defining joint probability functions, or joint PDFs. We'll then introduce the concept of joint distribution functions, or joint CDFs, followed by some examples of what these look like. So let's start by saying we have two possibly discrete random variables. So let y1, y2 be discrete random variables. We'll define the joint probability function, or the joint probability mass function for y1 and y2 as p of y1 and y2. So we now have two inputs to our probability function. What this gives us is the simultaneous probability, if you will. The probability that y1 is equal to some value little y1, and that y2 is also equal to some value little y2. Think of our random variables now as not just a single value, but ordered pairs. What are we getting with y1 and y2 jointly or simultaneously? Like other probability functions, we do have some restrictions on these. So first, the probability function must be greater than 0 for all y1 and y2. In the case of a discrete probability mass function, it must also be less than or equal to 1. Because this is a probability mass function with discrete random variables, the sum over all pairs y1, y2 with non-zero probabilities must be equal to 1. So let's take a look at an example. A local supermarket has 3 checkout counters. We have 2 customers who will arrive at the counters at different times. When the counters are serving, no other customers. So each of these customers is going to choose a checkout counter at random independently of the other. We'll let yi be the number of customers who choose counter I, so counter 1, counter 2, counter 3. What we'd like to do is find the joint probability functions of y1 and y2. So come up with a joint distribution for the number of customers at counter 1 and the number at counter 2. Now we'll start by listing the possibilities, and think of it like this. We have customer A and customer B who will choose counters independently of one another. So any one of these assignments is equally likely. Both customers could independently choose counter 1. Customer A could choose counter 1 independent of customer B, choosing counter 2, and so on. So we have a total list of possibilities here. What we want to do next is translate this list to the number of customers in each scenario. So the first scenario has 2 customers at counter 1, no customers at the other 2. The second scenario had 1 customer at counter 1, 1 at counter 2, and so on. Then our random variable y1 is highlighted in yellow. Here are the possibilities. y2 highlighted in blue. Here are the possibilities. Our joint probability function will look like this. So we'll go through and find all of the ways that each particular outcome occurs with respect to the pairs of y1 and y2. So for example, there is a 1/8 probability that y1 is equal to 0 and y2 is equal to 0. The last entry in this table is the only place that occurs. There is a 2/8 probability that y1 is equal to 0 and y2 is equal to 1, and so on. So we can set up each of these different outcomes. For any random variables y1 and y2, the joint bivariate distribution function, or the joint CDF, looks like this. We say that capital F, evaluated at y1 and y2, is the probability that y1 is less than or equal to little y1 and y2 is less than or equal to little y2. For discrete random variables, we'll sum. So for our example, let's find some values of the CDFs. Let's find the CDF evaluated at -1 and 2, the CDF evaluated at 1.5 and 2, and 5 and 7. So here's our CDF in the table below. Let's start by going through each of these possible outcomes, starting with the first. It's not possible for y1 to be less than 0. 0 is the lowest possible value. So for the first one, the CDF evaluated at -1 to 2, there's no probability that has occurred because we haven't actually observed anything where y1 is negative. Similarly, for the CDF evaluated at 5 and 7, that contains everything. y1 must be less than 5. y2 must be less than 7. So we have captured all of the probability there. Now let's zero in on the CDF evaluated at 1.5 and 2. So what we're looking at are all of the possible outcomes where y1 is less than 1.5. So everything where y1 is equal to 0 or y1 equal to 1. And y2 must be less than or equal to 2. So really these first two columns of the joint CDF are what we're interested in. If we add those probabilities up, we get 7/8. So let's move to the continuous case. We'll let y1 and y2 be continuous random variables with joint distribution function, or joint CDF, capital F of 1, y1, and y2. If there exists a non-negative function, little f, evaluated at y1 and y2, such that the double integral of this function returns the joint CDF, then we say that y1 and y2 are jointly continuous random variables. The function then, little f, is the joint probability density function, or the joint PDF. So we're actually here defining the joint PDF in terms of the joint CDF. It's the function that makes this integral complete. We have some results with this. So if y1 and y2 are random variables with joint distribution function, apologies for the non-formula type setting here, capital F of y1 and y2, then the following should hold. The CDF evaluated at -infinity and -infinity is 0. CDF evaluated at -infinity and any value of y2 is 0. Same with y1 at any -infinity in y2 space, 0. Essentially, what you can think of this, as long as at least one of y1 and y2 is below the bounds of support, we have not accumulated any probability. Property 2, once we have reached a value above the support of y1 and y2, so for example, the CDF evaluated at infinity, the probability, or the joint cumulative probability function, is then 1. We've reached, or we've accumulated up all of the probability. This third probability, or this third characteristic, 3, is actually something we'll talk about together in a group, but I do want to define it here. So let's say that y1 star is greater than or equal to y1, and y2 star is greater than or equal to y2. In order for a joint distribution function to be valid, this inequality must be satisfied. The CDF evaluated at y1, y2 star minus f of y1 star, y2, minus f of y1 and y2 star, plus f of y1 and y2 must be greater than or equal to 0. So whatever that region represents must be greater than or equal to 0. And again, we'll talk about what this looks like and what this tells us in class. So for the univariate continuous case, we take a look at areas under a probability density curve. Now, because we have two random variables, we'll be integrating over two random variables. So we'll need to perform double integration. This is typically a Calc 3 topic. So if you haven't seen double integration before, that's okay. I am more than happy to do a little review of it in class. Essentially, the idea is that we'll just integrate over both random variables. So the probability, for example, that y1 is between a1 and a2, and and y2 is between b1 and b2, is the integral over y from a1 to a2 with respect to y1. We'll take the integral from b1 to b2 with respect to y2. This setting up the limits of integration is probably the hardest part of this. Essentially, we're looking for volumes under a two-dimensional surface instead of areas. So suppose that a radioactive particle is randomly located in a square with sides of unit length. So if we have two regions within the unit square of equal length are considered, the particle is equally likely to be in either region. We'll let y1 and y2 denote the coordinates of the particle's location. A reasonable model for this might be the bivariate uniform distribution. So essentially, our joint PDF is 1 for y1 between 0 and 1, and y2 between 0 and 1. So let's first visualize this PDF. We'll find some CDFs associated with it, and we'll find some areas here. I'm going to sketch these using a shaded contour plot. So in my plot that you'll see, we have 1 everywhere, so that's the value for the joint PDF. So really, this is just a flat rectangle. In order to now find the joint probability CDF, or the joint CDF of 0.2 and 0.4, we want to take the probability that y1 is less than 0.2 and that y2 is less than 0.4. So y1 will integrate from 0 to 0.2. y2 will integrate from 0 to 0.4. Our joint CDF is 1. We'll take that integral with respect to y1 first. So with respect to y1, our integral is y1 evaluated from 0 to 0.2, which then becomes 0.2 dy2. We'll integrate that from 0 to 4. We end up with a probability of 0.08. At home, I'd like you to try this one on your own to set up the bounds of integration. You should get 0.1 for your answer. Let's take a look at a more complex example. So we have gasoline that will be stocked in a bulk tank once at the beginning of each week and then sold to individual customers. We'll let y1 be the capacity that is available after the tank is stocked at the beginning of the week. Because of limited supplies, y1 can vary from week to week. So some weeks the tank will be very full at the beginning, we'll have a lot available. Other weeks the tank will not be very full. We won't have as much available to us. y2 is in the proportion of the capacity that is sold during the given week. Now we cannot sell more than we have available to us, so y1 must be greater than y2. Because we're thinking of these as proportions, both must be between 0 and 1. So let's say our joint CDF looks like this, or excuse me, our joint probability density function, PDF. We get 3 times y1 for 0 less than or equal to y1, less than or equal to y2, excuse me, less than or equal to y1, less than or equal to 1. So the bounds or the support of this will look like a triangular region. We want to find the probability that less than half of the tank will be stocked and more than 1/4 of the tank will be sold. So this one will be a little trickier for us to work with, and that's because we have this y1 less than y2 constraint. So we'll need to integrate that into our bounds. So in order to find the probability that less than half of the tank is stocked, y1 is less than 1/2, and more than 1/4 is sold, y2 is greater than 0.25, we'll have to set it up somewhat like this. Now here I've chosen to take my integral with respect to y2 first. We can certainly change the order. We could do this dy1, dy2. We should get the same answer. If you integrate with respect to y2 first, y2 will range from 0.25 up to y1 because we do have that upper bound on y1. Once we have integrated out y2, then y1 can range from 0 to 0.5. So with respect to y2, we get y2 evaluated at 0.25 minus y1. We get something that looks like this. We will distribute the 3y1 across just to make life a little bit easier. Continue out this integration. We end up with 0.03. So there's about a 3% probability that less than half of the tank will be stocked and more than 1/4 will be sold. So we will stop here for this video. Again, the hardest part of working with these joint density functions is setting up the bounds and visualizing what these will look like. We'll get a lot of practice with those in the next class period. In the next video, we will talk about marginal and conditional distributions. See you then.